I hope we crop out the beginning.
Yeah. All the drinking.
Okay. Yeah. All right. Well, thanks for coming. A bit over time, I'll try and skim through it. This is something I've kind of been involved with for the last 10 years on and off. It's something that I figured might be interesting, in that we spend a lot of time, or I spend a lot of time monitoring what miners are doing or dewatering from miners, but in this case, the hydrogeologist is the miner, so it's a bit of a role reversal. Plus, it's a resource assessment, a water resource assessment, which I don't see happening too much these days because it's all allocated. It's quite well, I think. So that's the kind of terrain we're dealing with. That's kind of salt at surface, and you can see the brine, which is within half a metre of surface. I should mention that I'm from UK, so a well, same thing. So an observation well with a monitoring boat, I might get mixed up. So that's one from way back when, from the 90s, when it's kind of got crusted up. So we just want to do a bit of terminology, mineral reporting codes. What are they? Resources, reserves. There is a difference. Important parameters and how we assess them, in some examples. There's this guy Houston did a lot of work in the Andes, and he split these salars, or the salar is the Spanish, sarca is the Arabic term, one I'm more familiar with. And he split these into immature and mature. Mature being more thicker hair-like sequences and more uniform, whereas an immature salar is higher precipitation, lower evaporation. It's a lot more variable laterally and vertically. And it's not a hard and fast rule, so you can have both types in the same basin. So that's quite an interesting paper if anybody wants the reference later. A couple more pictures that show the terrain. That's not snow on the left, that's the hair-like at surface. And that one on the right is again in the Middle East, and that's a really interesting site actually, because there is oil at about 2,000 meters down too. So there was a bit of competition with the petroleum guys as to they discovered oil back in the 80s, but they didn't exploit it because that's a very thin surface. If you go through that half meter of halite, then you're in trouble. Bulldozers will get lost and all sorts. You can just go into the soft sand below. It's become a bit more interesting recently because BP drilled some horizontal wells, which made it more attractive to everybody. It's also very difficult to drive on. I mean, those small ridges are rock hard, so you'll kill your suspension in no time. That's actually an old seismic line that we're driving along. So the one on the right is a mature one. I'm sorry, immature. And the one on the left is mature, but you can't really tell any difference from surface. There's a couple more photos. They're doing a magnetic telluric survey on the right. And on the left, that snowman feature is in fact a bore. It's an artesian bore that wasn't sealed properly. That's the salt that's crystallizing out and getting wind blown to the left. So mineral reporting codes, they come under something called PRISCO, which I don't know what stands for, because it doesn't make sense in English anyway. Which is an international organisation, and each region has their own code. JORC in Australia and PERC in Europe, and Canada's got their own, and so forth. I'm more familiar with the Canadian one because that's more brine friendly, shall we say. So why do we have them? To make sure that exploration results are consistent, transparent and reliable for the investor. This is all about investor confidence. You, the miner, are trying to get investment from the bank or internally or whoever. And to make sure that there's a minimum reporting standard that details the value and the risk for the investor. That's all laid out in the codes, but what they don't say in the codes is that it's also trying to cut out fraudulent reporting. So Brines was a Canadian scandal. I think investors lost $6 billion due to poor reporting. And my own geostatistics teacher went to jail because he misreported he purposefully on acute mining, and then sold it on, and when the new investor turned up, there was nothing there to mine. So the serious fraud squad went and got him. Also, if you've seen the film Gold, this is similar. So that's the structure of a report. You've got to fill in all of those categories. Even if you say we didn't study it this time, it's too early we're only at pre-feasibility, so we didn't study economics or whatever. You've got to address all of those categories. And who can address them? You need to be qualified or competent. Now, what defines that is up to a point yourself. You need to be able to demonstrate competence in front of peers. You do it on a minimum of 5 years experience in that mineralisation. So in theory, I could go and report on a gold deposit, but I wouldn't know what I would be talking about. And you need to be independent from the mining company. And you do also need to be a registered professional member of a recognised body. So whether that's moving into the rest of hydrogeology or not, I don't know. But so I go into the UK version. Here in Australia, you don't need that. RPGOs, you need to be a member of the AIG for, I don't know, for some unknown reason. They don't request it. But I don't think that's rigorous enough personally, but that's up to them. So resources and reserves. Resources are effectively what's in place, and as you move down the scale, you've done more work, you've spent more money, you've done more surveys, you've done more drilling than you've been doing, and you move down from inferred to indicated to measured. And the investors will understand all of this. And to move across to reserves, then you need to study the rest of the stuff: economics, legal, government, what the government conditions are, social, environment, marketing, and a bunch of other things. So again, that table on the bottom left is from Houston. He's just recommended drill spacings for various, so for inferred mature, you only need a 10 kilometre drill spacing. If you want to go to immature measured, then 2.5.
Everyone?
It's all about value creation. You start off with a geological anomaly that nobody knows anything about, and as you spend more money on it, doing surveys and so forth, it becomes more valuable. And if the investor invests at the beginning, then it's going to cost them not very much. They invest once you've done all your surveys and got more confidence and studied all the economics and the legal side, then it's going to cost them more, but they've got less risk. So it's investor risk is high to begin with. But as you invest as a mining company invests in surveys and so on, doing what they're doing, then the investor risk decreases. So it's all about the investor at the end of the day. So the three important factors are the aquifer volume, how wide is it laterally, how thick, brine chemistry, how many milligrams of potash or lithium have we got. The specific yield is we're at the resource stage now, so we're just defining what's there. We're not defining what's economic, we're just defining what's there. So its specific yield is the important one. So it's a bit more complicated than hard rock, I think, because they're just dealing with tons and grade, and they'll probably refute that, but that's what I think. Yes, it's just S times C times B, and you come up with a number of how much lithium or potassium or whatever you're looking for. And one point that mining companies don't often understand is that brine will move. You start pumping it, it's going to move, and that's sometimes a bit of a difficult concept for them to understand. I think most of us will be across that. So specific yield is effectively what you can get out. So it's interesting. Well, JORC would allow you to report total porosity at one point. When I first got involved in this, they didn't have a comment on specific yield. They would just allow you to report total porosity as a resource. So whereas the Canadian NI 43-101, which I'm more familiar with, they specifically mentioned specific yield. So that's the one I've been using. JORC's kind of a bit more up to date, I think, these days. They do mention specific yield. And sorry, just to go back one, NI 43-101 has two independent methods of specific yield. So it's not just one method. They ask for two if you're going to use that particular reporting code, which can be well, we might see later, might be a bit problematic. Again, this is something that miners don't often understand. You're going to lose some brine in the middle simply because you can't get at it due to the cone of depression and so on. That's sometimes a difficult concept for them to get, because with a hard rock you just dig a hole and take it out. But aquifer volume we defined by drilling, obviously. It's high vertical resolution, but no information laterally. And they do a lot of geophysics to interpolate in between the boreholes. But obviously it has its limitations and needs to be done properly and by the correct people. Then it needs to be a correct choice of methodology. And I know there's certain people who don't think geophysics works, but it's generally because they have over expectations or broken contractual conditions can add to the case where the client won't allow you to change your methodology when you get to site and see what the site conditions are. For a whole bunch of reasons. So active volume is probably the easiest, even though it's open to interpretation. And this is that's a bore log, obviously, from, so that's an immature cellar. In fact, the subcurve, it's only about 8 meters deep, interbedded halite and sand, so unconsolidated sand, fine unconsolidated sand. So in that case, we did manage to get a bunch of samples from the sands to central lab analysis, which we'll come to later. So we're sampling the formation as well as the fluid. That sounding is from the same aquifer. It's an electrical sounding. You can see the base of the aquifer, 7 meters. Pretty good fit for the data. So it does work. It's pretty easy to do, quite cheap. It's probably not defining the top of the brine because it's not very accurate in the first couple of meters. So is that the top of the brine? Not entirely sure. The crew who were doing this, they were augering down and actually taking a brine sample in some instances. So I don't have that data. I don't know how well that correlates. Same aquifer again. This is a bit more. This is tomography, resistivity tomography. I think it'd be better than soundings, which are just 1D. This is 2D, but I'm not convinced. It doesn't really define the bottom of the aquifer very well, but it does define the edge of the basin. There are 2 possible faults there, which aren't evident on the ground. Yeah, I was a bit surprised. I would be surprised. It doesn't look as it's faulted, but you know, on the ground at least anyway. And so in this instance, we decided to can the tomography because it was too expensive and too time consuming. That particular aquifer is 30 kilometers by 60 kilometers. So if you want to go and define that with a 2D method, it's going to take you a long time. Some of the ones in the Andes are really deep, and that vertical scale is I think 400 meters. So it's the aquifer is 300 meters deep. That's in fact a gravity survey. They got a good fit with the. So the data is the dots at the top, and the fit of the model to the data is the line joining the dots. But that's a pretty good fit. That's another not so interesting, other than the fact that that's 700 meters deep, or 750, and they did in fact drill a deep bore into that and didn't touch the bottom. Still in here like 700 meters. So that is it economic to start pumping from 700 meters or not? That's that comes at defining that comes at a later point. It's just that's another magnetic. That's another method. That's a kind of pseudo 3D, lots of 1D points joined together. Another.
Is this all kind of aerial survey or?
No, it's all surface stuff. You can. I have been tried to be sold an aerial survey, but it's not. It might work on this kind of depth, 300 meters, but they were trying to sell it on 7 meter. It hasn't got vertical resolution, so the aerial. I think he was talking rubbish, but you know. So brine chemistry we can get from active pumping tests. Obviously, Houston, who everybody seems to follow, doesn't think that's a good idea. Largely because you're measuring a specific yield in the dewatered zone, not taking your sample from the where the brine still is. So you're not actually sampling the same spot. So I don't know anybody who actually doesn't do that. Everybody does it, but whether they agree with the paper or not, everybody takes samples from the computers. There's packet testing, airlifting, and discrete wireline samplers, so I haven't seen too much of that. So it's important to let the lab know that you're dealing with 150 milligrams per litre, or it's about 250,000 microsiemens per centilitre. It's important because not all labs can deal with it. You get crystallization during the analysis, and they just can't deal with it. So it's important that the lab understands what they're dealing with before you start shipping samples off to them. Otherwise, then it's a bit of a waste of time and money and effort. And obviously, you've got to do QA, QC, splits, temperatures, blends. All of this needs to be recorded because obviously the investor might say, well, what about this and what about that? And he's probably got an independent expert who's going to say, well, show me a chain of custody forms. So this is just an example of what you can do with the chemistry. This came from the immature salar that Sapra was talking about. These guys split they did some plots and came and decided that there were two different types of brine, or two different types, and they figured that they in fact wrote a paper, I think, on it. Suggested that some of the brine was coming up from underneath through the aquitard under artesian pressure, and some of it was maybe remnant seawater or rainfall runoff. But yeah, one thing I maybe should have mentioned at the beginning, obviously these brines occur over geological time. It's all an endorheic closed basin, so it obviously rains, rainfall runs in and then evaporates, and you get left with whatever was in the runoff. Specific yield, so pumping tests, something called relative brine release capacity, ball geophysics these days. I've seen one report with particle size analysis, but the paper, the reference they were using was from surface soils rather than. So I've only seen it in the one paper, in the one report. I don't know. Anybody else who's used it? That was from Western Australia. I haven't tried it personally. That's just a shot from an Actisolve graph from a pumping test we did. Obviously, it gives you a good idea of the bulk hydraulic properties, which ultimately define how you might extract this stuff. Are you going to drill a bunch of wells? Are you going to dig trenches? Other methods. Like I said, the sample that you take is not the same location-specific yield, so nobody seems to take any notice of that disadvantage. And your test needs to be in the third stage after the gravity drainage phase, which I don't think we're in there. So But unfortunately, the pumping well was dewatering, so we had to stop. So I still think that's in the gravity drainage phase, and consequently, we're not measuring specific yield. We've got a 1.5%. S in this case would equate to specific yield. But I don't think that was a successful test. Not for obviously hydraulic conductivity is fine, but I don't think it gave us a very good indication of specific yield. And there was only about a metre of drawdown, 30 metres away, and the pumping well was dewatering. So you're obviously not going to use wells to extract this, because you need a bore a well every 15 metres or something, or a 30 by 60 kilometre area. So it's not practical. So yeah, this pump test was from this. This is a bore log from the pumping well, and that the water would stabilise. It would fall until we hit halide, and then it would stabilise and then fall again, and stabilise and fall again. So whether we're actually ever in the third phase of the pump curve, I don't. So this seems to be the most popular methodology for measuring specific yield. Obviously, it's guaranteed to work. So you've got to take a core and then take sub-cores from out of the core and send them off to the lab. They need to be obviously encased properly in a plastic tube, and the ends sealed off and sent off to the lab. And they will put them in they'll put them in a system and vacuum pump them for 24 hours or so. And then the difference between the saturated sample and the vacuum dry sample is the release capacity. It's a relative release capacity if it's just water, but if there's brine involved, it's a relative brine release capacity. So you can test multiple samples at this time, and you can in fact measure vertical and horizontal K. Just got to get your subcores in the right orientation. And it does have a recognised ASTM number, so it does seem to be the most popular one that gets used. But again, there's few labs equipped to do it. Mostly seem to be in the States, so you might end up with a Donald Trump surcharge. And you do need to send them with a site-specific brine, so you need that they will soak the sample in before they test it. That's, I know some guys who forgot to do that and had to wait while they sent some brine off. This is a more recent methodology. That's a borehole geophysics tool on the right, on the left side. It's in his hand for a scale. As normal with these things, it's kind of developed in the oil industry, I think in around 1990, and then filtered down to the water industry 20 years later. So nuclear magnetic resonance, there's no the nuclear part refers to the protons in the hydrogen rather than an actual nuclear source. So it's been marketed as a BMR, or magnetic resonance, to lay people's fears. So it's just there is no radioactivity. It's just it's two powerful neodymium magnets at the base, which send alternating pulses, which cause a rephasing of the protons. And the tool measures the decay when they're relaxed, which is the curve on the top. That's the decay curve. And then that gets inverted to the middle image. So on the amplitude on the right side is free fluid volume, FFV, and on the left side is the bound fluid volume. So you can differentiate between what's the fluid that's free and what's bound. So the total of the amplitudes is the total porosity. And on the right is what's movable, and on the left is what's not movable. It can differentiate between clay bound and capillary bound water, but that seems to be a bit of a interpretation thing. It's easier to define between free and bound, but clay bound is a bit more open to interpretation. That's just it's not my example. I took that out of the manufacturer's website, I think. So we do get a total porosity independent of lithology, and we can divide that into clay bound, capillary bound, and free water. And also you will get hydraulic, but that's hydraulic conductivity is calculated as opposed to measured. There's two formulae, Schlumberger-Doll and Timor Coates. And it's also useful in pulsing gas. You can measure the free gas content. And one big advantage that I like is that it can be run in cased hole conditions, as long as you PVC, not steel. So as long as you get your bore design right, then you can go around and do a whole bunch of them all in one go at the end. As Ali said, last 2 months ago, whatever it was, it's very expensive. It's not cheap. If you're on an academic budget, get it. If you're trying to get some investor to give you some money, then I think it's a pretty good idea. And it is complex. I did hope to have some more data, but didn't happen. But maybe I'll get some more in future. So on this, this is 150 meters deep. So on the, it's maybe not that easy. Do I have a pointer? So in the second from the right is the specific yield from borehole magnetic resonance, which goes as far as 1. But that's a fractured halide, so I don't think 1 is entirely unbelievable. And then the red dots on the kind of right are lab measurements, and they don't match. Not very well. So the client decided they didn't trust the geophysics and didn't use it. But yeah, I would say the yield of close to 1 is achievable in fractured halide. And they also ignored the advice to case the holes and run it in cased holes, because the reason that data only goes down halfway is because the bores kept collapsing. So in this case, they had limited pump test too, because they basically couldn't get the fractured halide to draw down during testing. It was so conductive, so that hydraulic conductivity was so high they couldn't get any drawdown. So they basically relied on lab tests and And yeah, so did they get two methods? Probably not. Let's just back to the resources and reserves. Just a reminder of you do want to end up on the reserve side for your investor to be fully confident, because to get across from resources to reserves, you need to take all those modifying factors into account, which is where hydraulic conductivity comes in, because it can define how quickly you can get it out. Processing needs to be in there. Do you evaporate it? Do you put it through pollution columns? All the list, that's not even all the list of modifying factors that you have to study and put in your report. So one thing I forgot to mention is that the QPs are a team, that qualified persons are not just hydrogeologists, but we get the economics and the environment and everybody else involved at some point. Yeah, that's just a recap. Active volume, brine chemistry, specific yield, define the resource. Active volume and brine chemistry are, I'd say, relatively easy given budget, and specific yield is a bit more difficult, especially if you're trying to get two separate methods. And modifying factors move you from resources to reserves, from how much is present to how much is economically expectable. I was talking, it's probably not economic to start pumping from 700 meters. Those are the references. The Houston one is interesting. The Stormont one is just a description of the lab methodology. And that's it. End of scope. Anybody's got any questions or?
I have a question about the casing and the hull stability. What type of casing would you suggest, and how do you factor in casing influence? And that's why.
It's an electromagnetic method, so it sees through as long as it's PVC. Doesn't enter into it. Steel won't work. PVC, and they have certainly the supplier that I've dealt with in the past, they have equipment with different diameters. So the different diameters have a different investigation radius. So you can see beyond, as long as you get your design of the bore right, and so that it's wide enough for the tool to go in. The gravel pack's not too thick. You can see all the way into the formation. It's just a question of putting a bit of thought into it.
I have a question. Given that you're extracting around and dissolving part of the formation, I suppose that that means that the hydraulic properties are changing constantly over time as the process happens. Does that mean that will numerical models be useful in there, or do you think that it changes so much that it's?
Yeah, I forgot to mention, I'm sorry about that, I forgot to mention modelling. Modelling comes in when you're moving from reserves to resources. Sorry, resources to reserves. You need to do a numerical model at that point, because that will define the models and tell you how much you can get out economically. So yeah, but yeah, they might. I mean, this stuff's super saturated, so it's not going to dissolve too much. But because don't forget, it's been sat there for whatever, but it's been sat there dissolving the halite or whatever, and in fact depositing the halite. So it's not going to dissolve too much on its way out. But yeah, it would be And also if that fine sand, I'm sure that's moving around too. That's an issue they had at that site. They're keeping the sand out of the bore, out of the pumping.
And second question, is there a case where for extraction where they try and inject fresh water to dissolve even more, or is it usually just extracting whatever the content of the water brings and that's it?
Because of the evaporation sequence, the halite is the first to crystallize out. So there's no point in you're just going to be dissolving the halite. All of your economic lithium or whatever is in solution, because halite will be the first to deposit out. And in fact, halite is it's called a big problem, but you're going to get 20 times more halite than you are what you're after, which is the potassium or the lithium. And it's just a waste product, so what do you do with it? So it's a problem for some projects. It's just a massive amount of waste.
Got a question. When you were comparing the specific yield from NMR and the one from the pumping test, so NMR gives you probably.
I didn't get that far to the pumping test. I did hope that maybe for Melbourne. So the specific yield that I compared here. So the red dots on the right are from the lab test. It's a different scale as well. It's not that you see the specific yield from the lab test is pretty low. It's like 1 or 2% or 5%, whereas the NMR results are much higher.
Right. So, yeah, my point was that if they are comparing apple with apple, because NMR gives you the profile over the depth, so probably they have taken the sample from that depth. But
yeah, that's to getting a depth correlation correct. Yeah, but they are coring. I mean, so they should be pretty confident of the depth that they're taking their lab sample from. And the geophysics guys should be equally confident. So.
But a related question for that relative brine release method, what sort of size cores are people using?
Kind of that goes into the lab.
Yeah.
Kind of a couple of centimeters in diameter, 2-3 centimeters. It might be in that paper, stone paper. Kind of, this length and that diameter. So they suppose you get your core out of the ground and then take a plug out of the core.
All right, thank you so much. Thanks, Ian, and thanks everyone for being here. I don't know what everyone was.
Recording up?
Oh, yes.
Using like background music to start off.
Yeah.